This video will be about heat transfer through a wall structure. Very often wall structures consist of many layers of materials, and we would like to know how much flow, how much heat loss goes through a wall like that. And you will learn to understand the concept of U value of a layered wall and thermal bridges. Here is a picture of a building with an insulated building envelope, and the Q, the heat loss, the heat flow with the unit watt is of interest to know in order to make energy balance and knowing the effect necessary to heat up the building. And the heat loss is proportional to the exposed area and the temperature difference between inside and outside. And normally you should use the equivalent temperature on the outside as outside temperature. And it will also be proportional to what we call the U value, which is determined by the design of the structure. Using a formula, we have Q equal to A, the exposed area, times the temperature difference between inside and outside, and times the U value. So what is the U value of a layered wall? Well, we have seen this picture before when we have looked into the temperature distribution inside the wall. And here, this basic structure is the three layers with three different thermal resistances of each layer. And we know that the thermal resistance of one layer is equal to the thickness divided by the thermal conductivity. In order to calculate the U value, we use this formula to the right-hand side. We have U equal to 1 divided by the surface resistance on the inside, which has the default value of 0.13 square meter Kelvin per watt. And then we add the sum of the thermal resistances for each layer, R1 plus R2 plus R3. And lastly, the surface resistance is on the external side, which as a default value we're using 0.04 square meter Kelvin per watt. And the unit for the U value is watt per square meter Kelvin. And if we have more layers, we just add using this general formula down to the right here, where we just add more layers to the total sum of the surface resistance of the thermal resistances inside the wall. Here an example, we have from the left-hand side the plaster, 3 centimeters of plaster, then air concrete, 30 centimeters, and 3 centimeters of glass wool. And then we can have using the formula for the U value, we have 1 divided by 0.04 plus 0.04, which is the surface resistance, and plus R1, which is the thermal resistance of the plaster. The plaster thickness was 0.03 and lambda value 1, so we have 0.03 divided by 1. And for the air concrete, we have the thickness 0.3 and thermal conductivity 0.1. And the glass wool, we have thickness 0.03 or 3 centimeters and the lambda value 0.03 watt per meter Kelvin. And then lastly, we add the surface resistance on the inside, 0.13. And we got 1 divided by 4.2, which is equal to 0.25 watt per square meter Kelvin. And if we look at just 1 square meter of this wall, and we have temperature difference of 20 degrees, we'll have Q equal the heat loss 1 times 20 times 0.25, and this will give 5 watt. So 5 watt is flowing through the wall continuously. Thermography. This picture shows a thermography picture where you actually, instead of looking at the visible light, we're looking at the long wave that is radiated from the building surfaces. And if we have the same emissivity at the building surfaces, which is we normally have for regular building materials, the surface temperature is the only thing that actually determines how much long wave radiation that is flowing out. And this way we can detect spots where we have emitting a lot of heat transfer emitted. So if we look at the regular wall, we know that the temperature difference or the temperature drop on each layer is proportional to the resistance of each layer. We also can determine that the surface resistance on the external side determine the temperature drop between the outside temperature and the surface. And the same with the inside, we have a temperature drop there due to the internal surface resistance. So the temperature difference between the surface and the surrounding air, or the outside temperature, will be determined by the surface resistance and will be proportional to the heat loss. So the more heat loss flowing out from the building and the greater external surface resistance, the greater temperature drop at the outside of the building surface. So if we have a thermal bridge here illustrated to the right with a concrete floor going through a well-insulated wall, so we'll have very high heat losses going through the concrete because it has such a high thermal conductivity, and we have quite low heat losses through the well-insulated wall. So in the well-insulated wall part we'll have low surface temperatures, and while the area close to the concrete floor will have high heat losses and high surface temperature. So then we can actually see, using a thermography technology, see the high surface temperature where we have the concrete floor, or any spots where we have higher heat losses in general. And on the inside we also had higher temperature drops. We have lower surface temperature at the surface if we have high heat losses, high heat flows through the wall. And what we see in the pictures here are actually dirt formations where we have thermal bridges where we have colder surface temperature. And this is a quite interesting phenomena. So we have a kind of a soot or a dirt particle here to the right, and we have the air molecules bouncing around. And if such a particle is close to the wall where we have a thermal bridge, the air molecules close between the particle and the wall has less movements, is less energetic, they moves smaller vibrations than the air molecules in the warmer area on the other side of the soot or the dirt particle. And these molecules will bounce towards the dirt particle, but they will have more kicks from the warm side than the cold side. So slowly but surely the dirt particle is moving into the cold areas and will be stuck to the wall finally. That's why you can see dirt formation where we have thermal bridges. Summary. The heat loss through a wall is proportional to the exposed area, the temperature difference, and the U value. The outside surface temperature increases with increasing heat loss. The inside surface temperature decreases with increasing heat loss. Using thermography, the surface temperatures can be visualized and thermal bridges can be found.